Good evening, everyone, and welcome to African Women in GIS training. If you are with us today, can you say hi on the
Good evening, everyone, and welcome to African Women in GIS training.
Hi on the comment section. Hello, Juni. Hello, Emilia. We can see you. Hello, Fusaini. Thank you for joining us on day 4. Hello, Isaac. Welcome. Thank you for joining us today. Okay, as usual, we are going to dive right into the business of the day. So thank you for joining us through day 1. We are in the 4th day of the training, and it has been a wonderful one. And we appreciate our listeners and our participants who has been joining us for this program. Yes, hello, Alajide, we can see you. Thank you for joining us. So today, I would like to start by showing us a very interesting map here. This was produced by one of the participants, and we really were happy to see this. This is to show that we have already started measuring impact, and this is beautiful. The person that sent this is personal from me. So whether you have joined us or you watch the video later, I would reach out to you, and I have a gift for you, and I'll tell you what that gift is when I reach out to you privately. So although the map is not 100% accurate, but this is beautiful because to have someone who is a beginner in GIS to produce such an amazing map shows that there is an interest, and some people are also learning. So thank you very much. But because of what happened yesterday, we were trying to, combine a lot of activities yesterday, both the georeferencing, digitizing, and creating map. I think we lost track of some people because a lot of people were also practicing alongside the facilitator for yesterday. So we have a bonus. We have a Ponto bonus for you. We would like to give out 10 minutes from today's section to Damilola, a facilitator from yesterday. So we would like to give 10 minutes back to map creation so that we would be able to bring back some people up to speed. If we lost you along the line, if you have any correction or anything to do, you can, trace your step backwards. So we are going to take 10 minutes from the time for today to dive straight into map creation before we go into the business of the day. So as usual, today is day 4, and we are going to be covering introduction to remote sensing. This is a very beautiful topic, and I know a lot of people will be interested to learn more, and image classification. I know we have a lot of people who are interested in image classification, and so many of you have reached out to us. So this is the D-Day. We are diving right into remote sensing and georeferencing today, and our facilitator for today is Chidinma. She is a co-founder for African Women in GIS. This is Chidinma. She's going to be taking us on day 4, day 6, and 7, and today she's taking us on remote sensing and image classification. So without wasting much of our time, I would like to welcome Dami. Dami, please, can you give us 10 minutes of your time to give us a brief rundown on map creation again so that we can bring people back to speed? Thank you.
Okay, Thank you so much, Nina. Okay. Hi guys. So today we'll be repeating the map creation aspect of yesterday's training. So the first thing we need to do is to bring in our data. So we're going to bring in the shape files we created yesterday and the Nigerian map that we digitized to, just to show you how to design a map using both the vector and the raster data. But I'm just going to show you guys how to design a map. So I'm bringing in my data now. Since it's a vector data, I'll just click on the layer and add layer. So add vector layer. So I have to just pick the shapefile. So I have rivers. And then I'm going to add the polygon shapefile, so which is the boundary. Then add the line data, the polygon, the polyline shapefile, so which is the point shapefile, sorry, which is towns. So now I have the three shapefiles that were created yesterday. Okay. Then also bring in the raster data, which is the map that we just referenced. Okay, so I'm going to uncheck this for now, just to show you how to create the map. So to create a map in QGIS, we have to navigate to the layout view. So to go to the layout section of the QGIS interface, we just click on projects, then we go to new print layout, or you can press Ctrl P, just like this. Control P, and this will come out. So you're supposed to name your print layout. When you're creating it, there's a need for you to create a name for it. So let's just say before. Okay, and this interface pops up. Then you must save this layout. So just click on save. So now that we already have our layout view, we just need to bring in our map. And to do that, the icons on the left hand side of this interface is what we use to design our map. Everything you need to design your map is on this interface. So you can play around the interface and just look at what each icon does. So the first one is to pan. Let's click on it, just move around. That's after you've added your map. So let's add our map. So this icon, add map, is what we use. Just draw like a rectangle or a square, anything. And this pops up. Your map from the layout, the main layer interface shows up like this. So you can zoom in, you can zoom out. So if I go back to this layer, that's if I want a layer to show in my layout view and it's not showing just like this, if I want the raster data that we georeferenced yesterday to show, I just have to go back to the layer section and just check it like this. So it shows like this. So if you want to add any other maybe layer or something to just show on your map, you can always go to your layers and keep adding your files till you have enough files to show on your map. So for now, I'm going to uncheck this raster data, then go back to my layout view. So since I've added my data, you don't just want the map to show like this. You want it to really show well and maybe expand what the content of the map. So you can move the item, this square, by clicking on select and move item. So you can move it like this. But if you want to move the content, which is this shapefile inside the map itself, you have to use this other icon, which is move item content. So you can move like this, like this. Okay, so now I'm just going to increase the size of this shapefile. So just You can do that by going to just click on this, make sure it's active, then you can increase the size from item properties, then the scale. Just you can increase and decrease to see how this works out. So I'm decreasing from 52 to 39, but it's still not the way I want it to be. So I keep decreasing, maybe 20. You can see it's bigger, and then you can actually increase when this happens, just 25. Then I use my move item content to adjust it. So just make sure that it covers the entire area I want it to cover. So this works out well. So this is our area of interest. So we want to name the point.
Hello, I can see that her her network has been disconnected. So please kindly bear with us as we try to rectify that. Thank you very much. We can see people. We can see where you are watching from: Kenya, watching from Namibia. Ruva, we can see your comment. No sound. Yes, we are working on that right now to rectify it. Sorry for that. Okay, so I think her network has disconnected. So I think we would go straight in to remote sensing, introduction to remote sensing and image classification, which is the business of the day. I would like to welcome Chidima. Chidima, please, over to you, please.
Hello everyone, good evening. Can you hear me?
Yes, good evening. We can hear you. Welcome. Thank you.
Oh, thank you. Thank you once again, Nina. All right, I'll be sharing my screen in the next few minutes, seconds, please. Can you see my screen?
Yes, we can.
All right, good evening everyone and welcome to today's training on remote sensing analysis. My name is Chidim. Oh,
So the network has really been a big issue from our side. So please kindly bear with us as we are working hard to rectify this. Please kindly bear with us. Hello, Chidima, welcome back.
Oh, thank you. Sorry about that. My network went off for a moment. Hello, can you hear me?
Yes, we can hear you. Please go ahead.
Is my screen showing now?
Yes, perfectly. We can see it.
All right, thank you. Sorry about that. My laptop went off a moment. So for today's training, I'm looking at introduction to remote sensing and image classification. And once again, my name is Umo Chidima, and welcome to today's series. So what is remote sensing? Remote sensing is defined as the technology, the art and science of capturing information about objects, area, or phenomenon through the analysis of data acquired by a device that is not in contact. Underline that word, in contact with the object, area, or phenomenon under investigation. For example, your phone. The act of using your phone to take a picture is a method of remote sensing. Meaning that when you're taking a picture of something or an individual using your phone, you're capturing that person, you're capturing that image without being in contact with the person or with the image or with the object of interest. So in remote sensing is the same way. We use satellites to capture pictures on Earth. We use satellites to monitor events on Earth without being in touch or being in contact with that picture, without being in contact with that phenomenon. For example, in recent times, you have been hearing about forest fires, mostly in the western countries, example California. But you found out that they have been trying to monitor this forest fire using satellite remote sensing, satellite technology, being that they cannot come in direct contact with the forest fire on that kind of large on a large scale magnitude. So they use satellites, drones, to capture the image of the area, to capture what is happening, and to monitor the spread of the wildfire. So in essence, remote sensing helps man to monitor in real time or near real time the events happening on Earth. Now, remote sensing data and products. There are different types of remote sensing data, and these are dependent on what we want to use it for. For example, the nature and type of remote sensing information required in an application context are defined by the following. For you to go into the remote sensing analysis, you have a goal in mind, you have a problem in mind you want to solve. For example, land use land cover analysis. Now, your goal is to carry out a land use land cover analysis in an area. This will determine the type of data you're going to use. This is going to determine the type of remote sensing data you are going to use. Now, to carry out a land use land cover analysis, you require a medium resolution imagery, example, Landsat. Or you can use a high resolution imagery, example, spots, iconos, red eye. There are lots of them. So the analysis you're doing, you are going to do determines the type of remote sensing data you are going to use, both in type, both in the accuracy required, the temporal resolution, the spatial resolution, the SWAT width. All these things determines the type of data you will need to solve any inherent problem on Earth's surface. Now, attributes of remote sensing data are relevant for applications. Now, like I said, remote sensing and technology has been developed and classified under various types and specifications, and the type of project or problems they can handle. Taking for example Landsat again, we are used to Landsat Landsat satellites. Meaning that Landsat is more common, is free available, and is easily accessible too. Now, Landsat under spatial resolution is classified as being medium. Medium in the sense that we have low, medium, and high resolution imageries. For low resolution imageries, you have your SRTM, that digital elevation model. We have for medium, we have Landsat. For high resolution, we have iconos. We have our drone imageries too. Now, let me give for example. Subsequently, I'm going to show you the different types of images and where they fall into. But let's the attributes for you right now, just for now. Then under the attribute, we have again temporal resolution. Temporal resolution looks at how long, what the time period it requires for that satellite to revolve around the Earth. How long does it take a satellite to revolve around the Earth from point A and back again to point A? How long does it take a satellite to revolve from point A to point B, then point C, then back again to point A? That means that defines the temporal resolution. Some satellites have 16 days resolution, 16 days temporal resolution, whereas some have a day temporal resolution, whereas some have up to 30 days, 60 days, or 90 days temporal resolution. It depends on the need for it. Medium satellite, for example, Landsat has a 16 days temporal resolution. That means it takes Landsat satellites 16 days to revolve around the Earth's surface. It takes 16 days to revolve around the Earth's surface along a particular path. Then going again to spectral resolution means ability to sense in a wide spectral band. We all know about electromagnetic spectrum, and we all know that remote sensing depends on this spectral range or electromagnetic on this spectrum to capture images, to sense images. We have RGB and infrared. So most satellites that extend beyond just RGB, that's red, green, blue color, primarily known as the true colors. While some go beyond to infrared, ultraviolet, that is the things that the eye cannot see, but the sensors have the ability to sense those heats. Then we have FOV, that's global coverage, large coverage of the Earth's surface in a single sequence. This is done as SWAT. Some have 90 by 90 kilometer SWATs. Some have 500 kilometer SWATs, and also on. Then types of sensors are on board. We have active sensors and we have passive sensors. And all these sensors play different role in the environment in the sense that they capture different images based on their programming. Now, moving on, we're going to see the types of sensors we have. We have the active sensors and we have the passive sensors. Previously on the day one, Oluwadamide, spoke on sensors. Now, active sensors both emit a pulse of energy and detect reflected energy from an object. Example of an active sensor is an X-ray machine. We all know our X-ray machine. When we go to the hospital to take image of our chest, we use an X-ray machine to help the doctor to see the state of our bones and other internal organs. Then we have passive sensors. This one depend on lights or emissions from artificial sources like sun. Unlike active sensors, active sensors generate their own heat. They send it as a pulse. Let me show you this. Look at this diagram. This is a passive sensor. Now we have the satellite, we have the Earth, and the yellow we have as the sun. Now the sun is sending out an emission or a light or a heat towards the Earth's surface. Now a passive sensor depends on the sunlight to be able to sense the Earth's surface or a fissure. Example of a passive sensor also is Landsat. Landsat data are derived from passive sensors. So when the sun sends a pulse or emits a heat to the environment, the passive sensors senses the direction of that arrow, senses the heat being emitted from the Earth's surface, enabling it to capture what is going on the Earth. One of the disadvantages of passive sensors is that they are dependent on environmental conditions. They are dependent on environmental conditions such as cloud cover. Once you have a cloud cover covering the Earth's surface, the sensor will not be able to sense anything on the Earth. Unlike the active sensor, the active sensor sends its own heat or pulse to the Earth's surface, enabling it to bypass all the environmental conditions, be it haze, be it fog, be it rainfall, be it cloud cover. Thus, it can sense the Earth and capture information independent of any environmental condition acting at that particular time. So that we can see that active sensors are self-sufficient in a way. I define them as being self-sufficient because they don't depend on the environment to get their emission or their heat. They generate their heat themselves and they get the information they want for themselves. Example of an active sensor data you have is your SAR, synthetic aperture radar. Example, SROTM. SROTM stands for Shuttle Radar Topographic Mission. Its mission is to gather information on Earth's elevation. We have LiDAR. This data or sensors depend on themselves to generate heat and to gather information on the Earth's surface independent of any environmental conditions. That means they can penetrate through cloud cover and capture images correctly without any problem, unlike passive sensors. Passive sensors depend on the sunlight and depend on the picture themselves to be able to sense the Earth's surface. So when we have an issue of cloud cover, a passive sensor cannot sense the Earth. It cannot capture any good information. Are you with me? Please kindly indicate if you are If you have any question, please drop it in the comment section. I'll answer. Are you with me?
Yes, we are with you.
All right, now moving on to electromagnetic spectrum. We all did our physics. We all did physics, or at least have an idea of physics. We all know about the visible light, the ultraviolet light, the infrared, the X-rays, the gamma rays, the microwave, the radio waves. This spectrum exists in the Earth's surface. The visible light are the RGB that we can see. For example, our rainbow. The rainbows we see on the Earth on the sky, those are electromagnetic spectrum. Example again is our X-ray. When we go to hospital, we subject ourselves to X-ray to gather information on our internal body, our internal organs. Then we have the infrared. We humans cannot see beyond the visible light. Our eyes weren't developed to that extent of seeing beyond the visible light to the going into the range of infrared. For example, a owls, even dogs, some animals can see beyond the visible light into the infrared wavelength or spectrum or range. In the infrared range or wavelengths, we have various ranges. Put them again. We have the mid infrared, we have the near infrared, and we have the infrared itself. All these can be sensed by a sensor depending on the configuration, depending on the sensor's configuration. If a sensor has been configured to see both beyond the visible light into the infrared, it will be able to sense heat being emitted from objects. For example, again, during the COVID-19 pandemic, we also the infrared thermometer. I had the ability to take measurements of the body heat without being in contact with the body. Those handheld thermometer have been configured to operate within the infrared wavelengths, giving them the ability to sense heat within the infrared or to sense heat being emitted. Now, like I said, the sensors on board a satellite determines the wavelength the sensor can operate on. Some sensors cannot go beyond infrared, whereas some have been configured to go beyond infrared into the microwave wavelengths. Then after the microwave, now have our radio waves. This is basically where our radio stations operate on. In the radio waves spectrum or range, information has been disseminated that when a radio station sends out its broadcast, anybody tuning in within that frequency, within that wavelength, within that dedicated wavelength of frequency, can be able to hear what the radio station is broadcasting. Just like that, each sensors on board a satellite had been configured to operate within various wavelengths of frequencies, thereby enabling them to capture heat being emitted from the Earth's surface. Now, on the next slide, we have spectral ranges of sensors and their potential application areas. Please bear in mind that on this column table here, we have three columns. The first column is spectral range in microns, and this is being explained in second column, electromagnetic spectrum range and region where they fall in. Now, the various ranges or spectrum allows the sensor to capture images or capture information for a particular sorry the various spectrum allows the sensor to capture information or different pictures on the earth. For example, a Landsat sensor satellite sensor cannot penetrate below the earth surface, but it can capture most features or variables on the earth surface. But when you go to a past an active sensor, example is SAR data, synthetic aperture radar, radar data LiDAR, they can penetrate below the earth surface, allowing them to go deeper into the earth surface, capture seismic activities, earthquake, capture information on volcanic eruption or activities, lava flow below the earth surface, capture earth tremor, capture flood disaster, and not what do you call it, soil depths, and the information on soil moisture, root activities, plant root activities. All these features are dependent on the sensor and the configuration on the sensor based on its electromagnetic spectrum. Now, for example, the visible blue, number one, we have the visible blue allows the sensor to sense flood, inundation, ocean surges, and oil spill in an area. The visible green allows the sensor to sense deforestation and desert encouragement. The visible red allows the sensor to sense bushfire and desertification. Near the infrared spectrum, it allows the sensor to sense forest fires, dam breakage, pest infestation. Then the middle infrared allows the sensor to sense soil and vegetation degradation, snowfalls, haze, dust, hurricanes, tornadoes, etc. And the thermal infrared allows the sensor to sense earthquakes, wildfires, tsunamis. Then when you come to the K, we have Earth. You cannot allow, that's where the radar comes in. This is the sense, there is the range where the radar data, LiDAR data operates on. They have a monitoring Earth movement in the earthquake. That means they penetrate below the Earth surface to capture images on Earth movements, tremor, erosion, flood disasters, landslides, etc. So you see that each sensor has their strengths and weakness. Like Landsat, its strength being that it can help in land use land cover analysis, is free and kind of affordable, and anyone can utilize it. But when it comes to LiDAR and radar, they tend to be more on the high side because they perform better. They have a good strength that they perform better. They gather a lot of information that Landsat satellites cannot. So each of these satellites are there, and the use of their data is dependent on the project that one wants to undergo or undertake. So if you're going to do some works on crop monitoring, land use, land cover, you have to look for satellite that fall between the visible range, visible blue, to the green, visible and near infrared. If you want to work on land use, land cover again, you look for satellites or remote sensing data that fall within this spectrum, visible blue spectrum to near or middle infrared. You can be able to carry out land use, land cover analysis perfectly. But if you want to go deeper into looking at biomass or carbon biomass in an area, or you want to monitor tremor, earth tremor, or you want to monitor earthquake, you will not depend on satellites and Landsat data for that. You will look for a data that falls or operate within the K to P spectrums, being that they will give you the bands you can work with. The bands that have been sent, the bands contain the sensed information. That is your earth tremor movements. That is your earthquake, the landslide, the flood. This can be analyzed using the SAR or LiDAR data, radar data, and your Landsat cannot do that work. So you'll be depending on a active sensor data and not a passive sensor data. Now moving on, we are looking at classification of different types of satellite remote sensing satellites. We have an Earth observation satellite, example your Landsat. We have military satellites for military intelligence capture and gathering. We have communication satellites. We have meteorological satellites, and we have geodetic satellites too. All these are for various analysis, and all these are for various projects. It depends on what you're working on. If you're working on Earth data, for example, land use, land cover, watershed analysis, you'll be looking at Earth observation satellites. If you're into military analysis, military intelligence, you will depend on military satellites and the information they have gathered. If you're working on communication satellites, you'll be looking at telecommunication satellites and such. If it's meteorology, we have a lot of them. We have TRM data. There are lots of them that can help you to look at weather there's a climate data, such as rainfall, temperature, humidity, and so on. Now, image classification. The basic use of data from this satellite is for analyzing the Earth's surface and for information gathering. Another way of using this satellite data is for one way of using them is through image classification, what we call digital image processing. Before the information that are being gathered from the satellites are being put into use, they have to undergo processes called digital image processing. And one of them includes image classification. In image classification, we look at the way of processing a satellite data and assigning land cover classes to pixels. We know that in remote sensing, data comes in rows and columns, also known as pixels. Just like our phone has been classified based on 32 megapixels, 16 megapixel, 50 megapixels. The pixels means the depth, the resolution of those imagery. How sharp are they? How bright are they? How well composed are they? So within those pixels, we have information. Because each pixel of a satellite data contains information and have been assigned a number known as digital number, DN. This digital number that has been assigned to any satellite data refers to the spectral signature. It refers to the spectral signature of that picture within that pixel. So in image classification, you're saying that, for example, a digital number of 12 belongs to a building. That means that DN12 is equal to the signature of a building in an area. Now look at this image. Now look at this image. This is a satellite imagery, and it has been zoomed in so that you can see the spectral, the pixels it contains. This is a pixel, and the numbers we are saying 1, 2, 3, 1, 2, 1, 3, 3, 2. It means the digital number that the satellite assigned those pixels. This is a satellite data, and what we have here is a blowout showing the pixel and the number that the satellite, the digital number that the satellite assigned to each pixel, and this number assigned relates to the feature they are representing. Now, in image classification, our work is now to assign this, is to now organize this first image to this. Sorry, can you see my cursor?
Yes.
So the image of the work of an image classification is to define these pixel numbers and assign them a land use land cover class. In a way, you're organizing this first image to represent this. So, for example, the red color might stand for built up, the green color might stand for vegetation, and the blue color might stand for water body. Now, when you as an image analyst, or when you as a remote sensing analyst, you are classifying this, you assign the red color to mean feature 1. Feature 1 equals to built up. And you assign the P2 here to be feature 2, which is equal to vegetation. And you assign the P3 here, which is the blue color, to mean feature 3, which is equal to your water body. So when you now subject it to the different algorithms you have in image classification, it will now group it back onto this, like this. Now, all the images or pixels within P1 using maximum likelihood algorithm, for example, we group any pixel within a certain distance of P1 of your trained data to P1, then it does the same thing to P2 and the same thing to P3. So when you have successfully classified these pixels to this, you have successfully done an image analysis or image classification. That means I've successfully assigned classes to the pixels and what they reflect on the Earth surface. Now, types of image classification, we have supervised classification. In supervised classification, you select sample data or sample pixel of each land cover classes, also known as training data. The training data allows you to group your pixel, as we saw here, to here. The training data allows you to group your pixel from this to this. And for example of a supervised classification, we have maximum likelihood. We also have parallel piped. There are lots of them. Then we have unsupervised classification. Here you allow the software to cluster the pixels based on their spectral signature or DN. In unsupervised, the software itself will now find everywhere it sees 2 assigned to a pixel, it will group them as a cluster. By grouping them as a cluster, it assigns them a number, maybe cluster 1, cluster 2, 3, 4, 5, 6, and go on and so on. But you as the analyst, you not have to. What we do is to tell the software, I just need 6 classes or 6 clusters. It will use its own means, iterative means, to group those clusters into, or to group those digital numbers or spectral numbers into 6 clusters. If 1 and 2 are similar, it will group them as 1. If 3 and 4 are similar, it will group them as 1. If 5 and 6 are similar, they group as 1, and so on. Keep grouping them until you have 6 classes or 6 clusters. Unlike in supervised classification, you yourself will be the one to assign these clusters to a class, these digital numbers to a class, as we saw here. Now we have object-based image analysis. This is more kind of advanced, and here we now have on this object-based, we have machine learning algorithms. You have high resolution images come into play. So, but for now, we're going to focus on supervised classification and unsupervised classification. Remember, in supervised classification, you as the analyst have the power to classify these images into different classes based on the spectral signature or based on on their digital number. But on unsupervised classification, you give the power to the software to group these digital numbers or spectral signatures into different clusters as they relate to one another. But the only power you have in unsupervised classification is to tell the software that you only need 6 clusters or 6 classes, and it will try and group all those digital numbers into 6 clusters or into 6 classes. Most often, you will see unsupervised classification in basically data sciences. For when you don't have, if you're working on big data, it's better for you to use unsupervised classification than supervised classification. But we're not going into data science or machine learning algorithm today. We're just going to focus on the basic image classification. supervised classification and unsupervised classification using maximum likelihood for supervised and k-means or ISO data for unsupervised classification. Now remember again that in supervised classification you select samples for each land cover class. Then the software uses this training set that you have identified and apply them to the entire image. Whereas in unsupervised classification, the software first groups the pixels into clusters based on their properties. And these properties means the digital number or the spectral signature. Then when they are done classifying when the software is done with cluster, you now can now assign the names to these clusters to different land cover class. But here on unsupervised, you don't supervise the classification. The software does the work itself. But in supervised classification, you supervise the classification by assigning or by giving the software the training sites or the training data that will now be used to train the analysis, to train the image, sorry. Then examples of satellite data products. We have this one is the radar data, and remember that radar data falls under active sensor. That means in this image you will not see cloud cover, you not have issues of cloud cover or any environmental condition affecting the image. Now we have sports satellite data. Sports falls within medium resolution and also a passive sensor. Sports data is sent using a passive sensor. As you can see, the white patches here is cloud cover. That means the passive sensors are subjected to environmental conditions, and this portion of image now, the information covered by this cloud cover is already lost. Unlike a radar data or active sensor, active sensors penetrate beyond this cloud cover to capture images seamlessly. But passive sensors depend on the environmental conditions. So as in most often you will see passive sensor images or products having cloud cover, having issues of fog, having issues of haze or things like that. Now in this example of a Landsat data is a low or medium, not low, is a medium resolution imagery that help you to sense the environment. And this from what you have here, you have this white patches represents a sand beach, and this purple here represents a mud flat. Then again, when you're running image classification, you must to an extent have an idea of your environment. It helps you to run that supervised classification. You must have an idea of the environment. You must have an idea of what the spectral ranges of different pictures on the Earth's surface. Always have that in mind, that you as the analyst, you must have an idea of your environment or where you're working on. It helps you to classify or train those data effectively and perfectly without having issues. Now, this image of an airport was captured using a high resolution imagery as satellite. Sorry, for example, Iconos. You can see the building perfectly. You can see the aeroplane perfectly, well outlined. Using this image, you can do object-based analysis or object-based classification, because you can see the objects, so it's easier for you to classify them based on their feature. This is a SRTM data, that is digital elevation model. This is an elevation model of an area, and this also is captured by an active sensor. Now we have another high resolution imagery here too. We have now here we have a medium resolution imagery that can belong to a Landsat or sports, and so on. And this image here might also be captured using a drone. Oh, sorry, not yet. So these images here are captured using different sensors on board different satellites, and for different purposes. And they are also on a product of the two different sensors we have, both passive sensor and active sensor. Here we have a passive sensor. Here we have an active sensor. Even though these are high resolution imagery, but they also fall within the passive sensor and can be conditioned to environmental conditions like cloud cover, like snow, like fog, like mist, like haze. The image can be distorted despite it being a high resolution image, unlike the active sensor products, that's the DEM elevation model. This was captured independent of whether there is a fog, whether there is a cloud cover, whether there is any environmental variable occurring at that moment. It doesn't matter to the satellite. It captured its image perfectly well and clearly. So this brings us to the end of image classification. But I will take you again. Hold on, I want to open up my applications. I won't go deep on this because I've been touched by okay. Now, these are some examples of a classified data or classification analysis, image classification analysis, and this for gully erosion within some states in Nigeria. And this data was gotten from Nigeria Sat1. Using Nigeria Sat1, the analyst was able to capture or identify the different gully erosion sites within this area. Even though that it doesn't particularly shows where the gully itself is, but it gave a general idea or overview of the locations of where these um, gully erosion is occurring. Now, over here we have an example of a land use land cover analysis that was done within a floodplain. Now, from the legend, the analysts classified built up as being red. So that anywhere you see a red color, know that place is a built up environment. Then blue color was assigned to water body. Anywhere you see a water body, anywhere you see a blue color, that means there is a water body present there. Then the green color was assigned to vegetation. So anywhere you see green, assign green color, it means a vegetation is present there. Now, one of the importance of image classification is help us to run change analysis over time, change detection analysis over time. It helps the user, it helps the analyst to discover the change that have occurred in the environment over a period of time. For example, the image used in this picture was gotten from Landsat 1987. We found that the Landsat was developed or launched in 1972. I mean, it has a long range of years and data available, enabling one to go back in the past years to discover what happened then and compare it to what is happening now. Now, using a satellite image, you can identify changes that have occurred in the environment. You can look at growth, urban growth, for example. You can look at floodplain changes. How have this floodplain changed over time? You can see this red polygon here to identify or a floodplain. So, for example, how have this floodplain changed over time? Is it decreasing? Is it increasing? Or is it remaining the same? How can we know if not through the use of remote sensing? Going back to the previous years, at when maybe, for example, looking at urban growth in an area, it said that this city was formed in 1990. How was the environment before 1990? You can go back as far back as 1985 to get the status quo of the environment. Now, in that 1990, how was the environment? Is there any changes? Had any changes occurred at all? And after that 1990, going forward to 2000, what has changed? And these changes can be done at 5 years interval, 10 years interval. It depends on what you are trying to achieve. Now, let's use a 10 years interval, for example. I'll go back to 1990 to use that one as a base data. Now, I'll come again to 2000 and analyze the image of that same location for 2000, and I will check with 1990 to see if changes has occurred and what is the magnitude or rate of that changes. Then I come again 2010. What has changed? What has occurred? Then again to 2020. These are 4 epochs of 10 decades in between them. Now, using these 4 epochs image data, I can be able to analyze or detect any change that have occurred within that environment over this period of time. Now, it can help me to look at urban growth. How has this area developed from 1990 to 2020? What is the rate of development? What is being lost? What is being gained? All this can be answered through image classification analysis. Now, this what we have is 1987. Going forward, the analysts have 2000 image. Take note of vegetation, for example. In 1987, this white areas is probably a bare land, and we have few vegetation cover, the green. Then in 2000, we have the red, the red color here, that is the built up. You can see that the vegetation increased from 1987, between 1987 and 2000. Between 1987 and 2000, the vegetation of this area increased, and the floodplain, the water body, decreased. Go back again. Here is county. We have the green. We have the urban areas. We have the water body. Look at the spatial coverage of these different classes here. This is 1987. In 2000, the water body has decreased in spatial coverage, whereas we see that the urban area, the build-up is increasing, and we have lots of vegetation cover in 2000. Then moving forward again to 2010, wow, our vegetation is lost. We have more of built-up areas, and the water body is further decreasing. Now, built-up areas defines to any artificial surfaces, be it your roads, be it your buildings, anything that is artificial, that is not natural, is built up. It's being classified as built up. Now, you can see the magnitude of change that occurred between 2000 and 2010. In 2000, we have more vegetation cover. In 2010, we have more of built-up areas. We have less of water body. We have less of vegetation cover. So, reading these three images, I'm data now, results now. It can be you as an analyst can now be able to infer decisions and infer conclusions that built-up or urban growth in the area is at a high rate, and that water bodies is being depleted, and that vegetation is being depleted. So that most of the natural resources here are under extinction or under threats. Because for an ecosystem to be balanced, everything in it must be at a constant equilibrium or a constant balance. If one is higher than the others, we will have what we call ecological imbalance, and this affects the environment. Now, you as an image analyst, your work is not just to interpret the results. You can also apply your knowledge, be it in geography, be it geology, be it in whatever you specialize on, to infer decisions and conclusions from the image or from the analysis, from the results gotten from the image analysis or classification. So I think that brings us to the end of this session. Thank you. Now, since I will still have some time, I'm going to show us on the various ways we can get on the various sites we can download this satellite imageries for different analysis. Sources of data for different analysis. Are you with me?
Yes, we are with you.
Any question they want me to answer?
Yes, we have a couple of questions. Someone says, can you hear me?
I can hear you.
Okay, someone says, what is the independent way to deal with band combinations while dealing with satellite images without depending on the previous combined one sample for easy interpretation and classification?
Oh yeah, sorry. I think I skipped that when I was doing the. When I was introducing the image classification. But during our next class on language line cover analysis, I'm going to point it out. We have the false composite, we have the true color composite. It depends on what you want. But for most analysis, we use false color composite. For Landsat, we have the bands from band 1 to 10. For Landsat 8, we have up to 11 bands. So for the first color composite, we use bands 5, 4, and 3. And these are red, blue, green, and blue bands. So I'm seeing on the next class we're going to have on language line cover analysis. I'm going to point out the different band combinations. Just hold on a moment. Now, before we go into band combination, let me show you how to download your data and where to download your data from. Now, this is the for Landsat and Sentinel. I normally use this landsatloop.usgs.gov to gather my data. Now, in sourcing for data for analysis, like I said, it depends on what you are working on what you want to work on. Now, for our next part, which is land use land cover analysis, we're going to be using Landsat data for our analysis. And we're depending on Landsat 8. That's the sensor. So in this website, it allows you to state the year you want to work on. For us, we're going to work on from 2020 to 2021. So any image that falls within this year, you can work with it. I've shared the link to the coordinator, so she will share it for you on YouTube. So here, you state the year you want to work on. 2020 to 2021. You state the months of interest. Now I'll be going to October. Why did I choose October and not now again, bear it in mind that when you're running an Landsat, when you're running an image analysis, the years, not the years, but the time of the month matters a lot. The days of the month or time of the month matters a lot. For a language line cover analysis, it will be depending on images gotten from between November to February. Why? These are dry season. for us in Africa. For outside is the winter. And in this period for Africa in dry season, we have 0 or lesser cloud cover occurrences in the atmosphere. That means the image you'll be getting at this particular month is going to be clear. That means you won't have issues of cloud cover. Assuming we put an image we put the months to be July, June, August. These are peak of rainy season. And at the peak of rainy season, we have more of cloud covers. So to prevent the issues of having your image being covered by cloud, you go to, and for us in Africa, we choose our data from months from November to February. These are the peaks of dry season that have lesser occurrences of cloud cover. So here, I've started the year I want to work on. I'm setting the months I have in mind that will give me a lesser cloud cover. Then over here, I'm going to say the maximum cloud cover I want is 10% or less. 10% or less is better. If you can get 0% cloud cover, perfect. So this, you have to keep it in mind. The months of the year matters. The cloud cover percentage matters. If not, if you download an image of 90% cloud cover, that means 90% of your image is being covered by cloud, and you cannot use that image to do any analysis. So is to be on a safe side, you select 10% or less. Then the sensors we are working on, Landsat. You can choose to Landsat 8, you can choose to Sentinel-2 or Landsat 7, depends on the year you're working on. If I were to work on 2000, I won't choose Landsat 8, or rather I will choose Landsat 7 because it covers the year I want to work on. But since I want to work on 2000, 2001, I'm going to choose Landsat 8 as my sensor. Then clicking on OK. This arrow allows you to navigate here, select the attributes you want. So clicking on next, this will allow the image to load. The image loading over here will now it's still loading, so we'll give it some time to load. How to display the image they have for this area I've zoomed into. Now once the image load, it will come over here. It will be displayed here. All the scenes available will be displayed here. That allows you to choose the one you want to download, then you go on to download it. So I think we are going to stop here, and you go home, you practice on this. Try and download an image from this software, from this website, so that next time we meet for land long cover analysis, we are going to be working with the image you have downloaded. So I will stop here and give over to Demi to take over the content.
Thank you very much. I think we have time to. I think we still have time to take questions. So, with your permission, I would like us to take some questions.
Okay.
Okay. So, back to the same guy that asked. So he says, what I was asking was, how possible can I combine bands myself without looking into or considering already made band combination catalog? So I think what he means is, how will he do a classification without using already made classified bands or imagery? So like a fresh classification, what's the best method to go about it?
Image composite or image and band composite, it depends on what you want. It's not or allow the word strict or restricted. It's not restricted. Yeah, most people use 432 first image composite for their analysis, but most people depend also on true color composite. So it depends on you what as an analyst you want to do and how which one better helps you to identify the features you're trying to classify. For one,
Okay.
someone might be
So
okay using first color composite and they can easily identify the features on the earth surface. But someone might not be due to maybe being color blind or having not being able to interpret that, they can use another color composite that suits them better, that brings out the feature they want to classify better. So it's not restricted. You can play around with the band composite and get whatever get any color you want that can best show you the features you want to classify. I don't know if I answered the question.
yes, I think so. I think in summary, you are advising he goes for supervised classification, especially if he knows the area he wants to classify. So it's better you look
Yes.
in through the imagery, you know the area, you know what exists. So that's the supervised classification. So I think it's best to go for that. So the next question is, were those images gotten through remote sensing?
Yeah, which of the images? The Landsat?
Yes, I think she's asking about the satellite images.
Yes, 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 they were. Okay, since we still have time, I think I can share my screen on showing you the features that we can be the plugins we can use for we will be using for the what they call it, for the image classification in QGIS.
Okay, sorry, one more question. Maybe I think this question is also important. So someone is saying, if I'm using the unsupervised classification, can I get the required output I need after the classification?
Yes, it depends on it depends on how you can be you able to interpret. Because for unsupervised classification, it's not mostly advised to be used because the software clusters based on digital number. So at times those clusters might not align with the goal of the analyst.
Okay,
I might be
so
looking at
I hope. Okay, go ahead.
okay, for example now, maybe I want to classify an area using a supervised an area I want to generate vegetation, I want to generate open surface, water body and built up. Now, using supervised classification, I can be able to generate this data, this training sites and these classes. But when it comes to unsupervised, it's unsupervised. I mean, you are the mercy of the software. When you give it a poor range of a number of classes you want it to generate for you, you might find that the features you want are not the ones it has classified.
Yeah.
So that is the issue with unsupervised classification.
Okay. So I think you wanted to proceed to something, but before we move ahead, I think I can add something. Maybe it will be covered on the day the actual classification will be done. So for the viewers, maybe you can exercise some patience. I think some people are getting more interested in the remote sensing and image classification. So um, can you calm down on your curiosity? We have the 6. We are going to do the land use and land cover classification. So you get hands-on practical on that. But for the person asking if you are going to get the required output, actually, irrespective of the classification you are doing, there is also an approach you can use. So they call it evaluation. So you have to assess your classification, and the value you get at the end of the assessment should be able to tell you how accurate. So it's called accuracy assessment. So the best way to do accuracy assessment is to divide your data. If it's supervised, for instance, you go and do your sampling and collect the particular type of land use or land cover in that area. You split your data into 2. So the first part is going to be 70% you are going to use to train the data. Then you don't use the remaining 30%. So it's random sampling. You split it into 2, 30% and 70%. So when you are done with your classification, you use the remaining 30% to run your evaluation to see, yes, these ones actually fall at the exact place they're supposed to fall. So the percentage of your accuracy assessment should be able to tell you if what you have classified is very okay. So the higher the accuracy assessment percentage, the better your classified map interpretation is, because most times what you see in map, you just see, already classified map. It can be misleading. So, but if your accuracy assessment is high, it shows that yes, what I've actually classified is giving me the real ground truth classification that I'm looking for. So I hope by the 6 you get to know much in depth about land cover classification. So please, Chidinma, maybe you can proceed.
I'm trying to find a PowerPoint I have to show you.
Someone just said you have not answered my question. What is the question? Okay. I think on band combination. Let me see if I can go through. This is sheet 2. How possible can I combine bands myself without looking into already made band combination catalog? How can I combine them? Yes, I think it is the way you have asked the question. So band combination is, I don't know how to explain it to you, but if you are doing your classification and you have already picked a particular selection, let's say you pick green, you look at your satellite, you pick any place I have this color, I represent it as tree or forest. Anywhere I see this color, I represent it with river. Or anywhere I see this watercolor, I represent it with river. So you pick specific samples from different bands. You don't need to pick all the bands in the satellite imagery. So if you have, let's say, 7 classes in that imagery, you pick enough samples from each and every land cover you want to classify. So with that samples you have picked, that is what you are going to do. So automatically it's going to combine all the spectra indices, that the bands for those colors you have selected already, to show that okay, this is tree and this is water. That is now what you are going to use to classify your data. I don't know if that has answered your question.
Let me come in. Let me come in then. Let me come in then.
Okay. Yes. Okay.
Okay. Now, I don't have the column here for the table for Landsat, but I can show you what I have here. Now, each band of a satellite of Landsat falls within an electromagnetic spectrum. Each band of a Landsat data falls within within this spectrum. Now we have the visible blue, we have the visible green, and we have the visible red. we have the near infrared. In Landsat, these are the most these are the most important bands in Landsat. So any of the bands in Landsat that falls within this range can be used for image compositing or for band composite for for classification. Now, if you want to work on land use land cover, the visible blue shows the flood. That means we might not actually use it because it doesn't actually, it won't show us what we want. Now we look at the other bands. We have the visible green that shows deforestation. What they have in common? The visible red shows bushfire, that shows the desertification and defoliation. The near infrared shows the same thing. So that means these three bands or these three image region spectrum can show or give us this information on land use land cover. That can give us an information on vegetation, on water, or on built-up. So that any band that fall within this range can give us the information that can be used for classification. But if by peradventure you're not okay with this, you can go on to mix any of these, maybe middle infrared with red and green to give you a combination. Or you can go at using the green, visible red, and near infrared here. It can help in settlement landscape, urban area change analysis. When you combine a band from here, from this one, with this or with this, as you want, so far it can give you or show the features you want. You depend on the spectrum the band falls in to carry out your band image and your band composite. I don't know if I answered your question. Hello. Nina, are you here?
Yes, we have asked him to share more light on the question he wants us to answer. Then, but while we wait for that, maybe you can go ahead with any other business. Someone says, is it possible to show the different QGIS tabs used in image classification or an example using the software? So maybe you can answer that to them.
Okay, yeah, let me show my screen on that so they can even download the plugins we will need for the analysis too.
6. Yes, that will be done on day 6. So she will share the screen and show you the plugin for the image classification using QGIS so that you can familiarize yourself with it ahead of day 6.
All right, so I'll be sharing my screen again. Can you all see my screen?
Yes, it's still loading. Yes, we can see your screen now.
Okay, now this is a blank QGIS screen. Don't mind the different this I have there. Now for hold on, let me now this is a blank QGIS. Now for our land use land cover analysis, we'll be using semi-automatic classification plugin. one of the plugins that allows one to carry out a land-use land cover analysis in QGIS. Now, how can you access this plugin? Because one thing about QGIS, it doesn't come pre-installed with extensions. You will want to go to the database to download the plugins you want to work with and customize your interface as you want. If you want to customize your extension as you want, unlike ArcGIS, ArcGIS will come with already in pre-installed extensions, so it's kind of limiting your flexibility. But in QGIS, give you a blank check and a bank that say go in, take whatever you want, or customize your extension as you want it and as your analysis or capability. Now for land use land cover, over here we have the plugins. So I'll click on manage and install plugins, allow it to load. So we're here. Oh, now for the land use land cover analysis, for the land use land cover analysis, we'll be using this software and this plugin, semi-automatic classification plugin. I was thinking that my plugin will load as a whole, but it did not. So
Okay, while you are doing that, I think when you are done, there's a comment on how to download the imagery using the land link. So you can, I don't know, maybe she missed it. Try to come back to the video. There was a section she showed how to download the imagery. I think that is better.
okay, all right. Now when you go to your QGIS plugin, remember the plugin tab is here. Click on manage and install plugins. It will load. Unfortunately, mine just didn't load the whole database. So these are already the plugins I've downloaded that I'm using for my analysis. The best way to search for it, when you come to all, you click on search, type the name of the plugin. Once you type it, it will keep filtering it out until you get what you want. So you go for semi-automatic classification plugin, this. So when you select it, it will tell you to install. I've already installed it already. So the install plugin will here. You click on it, it will install. Once you're done, check again for SROTM downloader. This to help you to download SROTM, and we'll be using it in our subsequent classes too. Then for SWAT, key SWAT, this one is going to be a little bit problematic for you to download, but I'll show you how to do it later. But for now, we're focusing on this semi-automatic classification plugin. Once that's already installed in your, you have already downloaded the plugin, you click close. Now you now come to your view. Normally it ought to load automatically, but being that I've already loaded mine, I have to uncheck them from my panels. So you come to view, come to panel, check for.
I think your screen is only sharing QGIS, not the entire screen. So once you select view, we couldn't see anything.
Ah, okay. So let me go back again. I'll stop sharing for now. Is it okay now? Hello.
Yes, it's okay now. We can see.
Okay. So when you go to view, go to panels, check the SCP doc, then go to toolbar, check on working to this, check on this again, SCP edit toolbar. So here we can also let us explore the plugin. But the plugin can also help us to download Landsat for those asking on how to download Landsat. So I'm going to show, I'm going to take you on that. Now, and these are the different extensions or the different tabs within the SCP plugin. I see you can download Landsat, download Asta, download data, you can download Sentinel 1, 2, and 3. Yeah, you can even carry out random forest classification, unsupervised classification, and lots of them. So you come here and you click on it to bring you to the main interface of the plugin. In this main interface, you see band sets, you see basic tool, algorithm, band export signature, import signature. You will see download products. This is where you can download your Landsat SROTM from again and Sentinel. Then you see pre-processing. It allows you to pre-process the image to remove noise, to remove haze, to remove whatever you have to remove, apply atmospheric correction to create band set and create virtual band sets. Then you have the post band processing, band combination, classification, clustering, PCA, random forest, spectral distance. You have the post processing. You have the accuracy, as she said, accuracy assessments. This way you have to check how accurate your classification was or is. You have the dilation, class signature, classification. You have band calculation. Want to calculate bands. You have batch, you have settings. You can set your processing settings here. User manual. Oops. Then, now for downloading the products. Apart from using the Landsat look, the one I showed you here, this one here, you can also download your Landsat from the semi-automatic classification plugin, from the SCP plugin. But it's required that you should have a login details from USGS. That's for Landsat. For Asta, you register with Earth data. For Sentinel, you register with Copernicus. But if you don't have this required information of login data details, you can use or click on the alternative search. This allows you to download without using the authentication. Now, when it comes to search, are you with me?
Yes.
Hello. Okay. Just like unlike the Landsat look, you can easily search for the parameters. I mean, for the Landsat, using you define your parameters here. Over here, it is the upper left for your X and Y, and the lower right for your X and Y. But we will not be using this. If you don't have the details of this upper left, Y, and upper lower right you can use this. But for before you come out to here, let me bring in the data so you can know where we are working on. Give me a moment, please. I get layer, vector layer. Now this data is already georeferenced or stationed in an area. So we can use this as an ROI, area of interest, region of interest, to be able to download the Landsat data. Now, coming over here now to use this, since I don't know my upper left and my lower right coordinates, I will use this. This will help you to set this lower right, lower left, and lower upper left and lower right coordinates. So when you click on this plus sign, you come to your map interface. You left click, drag, right click again. Now, this bounding box, this red bounding box have identified the area you're working on. But in any case that it doesn't really cover, you see that some areas here are not covered, you can as well click, you come back again, you click extend your hand up here. You see, by extending your hand, you have already covered, accounted for that other space that was left. You can also do the same here too. Sorry. So we have already identified our area or region of interest. Then going back to this, you see that it has automatically loaded the upper left and lower right coordinates. This has automatically loaded the upper left and lower right coordinates. Now we now go on to select the products. Our products, we are going to use either Sentinel or we use Landsat 8. When you select the products, you will check the date again, just like we did on Landsat Look. You check for the dates. What we have is 06, that is June. And I've already told her that June data for analysis is not good. So we go for, say, November 1st, 1st of November to 2020 to February 28th, 2021. These are dry season, and our land cover, our cloud cover is going to be lesser. So over here again, we have maximum cloud cover percentage. You can increase, you can decrease it. So I'll be going for 10%. Then the results, how many results do you want to be shown? Maybe we can use 20 or what have you. And then say click on find. Once you're done setting the parameters, you click on find. Now, this is the image it gave us for that location we clicked on. Then again, in the case where you don't have a ROI, you can click on add OpenStreetMap to the map. When you click on it, you have OpenStreetMap here. So with this OpenStreetMap, you can go to your where you're working on, navigate to where you want to work on. Now, this is Calabar in Nigeria. Assuming this is my study area and I want to work here. Now, I'll give you an example. I'll give you an example when you have a study area shapefile. Now, I think there's an example where you don't have any study area shapefile. So, going back again to this place, you will click on this OSM. Once you click on it, it will add the OpenStreetMap to your interface. Now, when you navigate to your study area where you want to work on, you go back again and click on this plus sign to generate the upper left and the lower right. Now, clicking on this, I'll go back again. I'll left click. Now, you notice that it has given me an area of interest.
So I think
My
yes. Can you hear me?
I can hear you.
Yes. I think we are running short of time, and the training is quite interesting. I don't know, depending on our viewers, if we should produce or proceed, or wait for the land use classification. Then we can go in depth to land cover classification. We have 2 minutes to go.
Oh, okay. So I think they can now on their own
Maybe
they can now on their own generate this one. When you once you click on the one you want, it will give you a preview. You can run. What you do by run is to download the image you have clicked on. So once you download the image, it will load automatically here. So, but due to time, I will be stopping here today. So, when you go home, please practice. Practice. So, when you go home, please
okay.
practice. Thank you.
Thank you so much, Chidinma. This section was very informative. The same Shitu is asking the same question, but because of time, the question you are asking is actually not covered in our schedule. GIS is a very broad area, so what you are asking is photogrammetry, which we would have covered from the initial time of the lesson. So we really apologize for not covering that. We are trying to see how we can touch on most important areas that people might want to use in their everyday analysis. So there you can still research on different. I think what you mean by decomposing the enhancement. So you can look into photogrammetry and see there are different ways you can do that enhancement. There are different analyses you can use for that. So we are sorry we couldn't cover that topic in our section. So tomorrow we are going into buffer analysis and hotspot analysis. I have shared a link. We noticed that most of the people participating in this training couldn't register from the beginning, and we have closed the registration. So right now we have made it open again so that people can register. This is because at the end of the entire section, we are going to give out just one or two assignments just to test and see how much impact this training has gotten across to people. So we will be sharing. I've shared the link. If you check the comment section, I've shared the link to register. Please, if you've registered before, don't register again. So that when we are sending the assignment, we'll be able to reach out to you, because after the training, we don't have any other way to reach out to you. So please register if you have not registered. And tomorrow we'll go to book analysis. Next tomorrow, if you have any question from this section, keep it for day 6, which is land use and land cover classification. We'll try as much as we can to cover your questions. But please, again, I apologize because of time constraints. We might want to end this section now, because we have already promised our viewers 2 hours per day. And we know 2 hours is not going to be enough to give you all you want. But please, at your own convenience, please try to learn more. We have always tried to send in some of these materials every day for the previous lessons so that you can get hands-on training, including the data set. So please, if you at your spare time, try to practice because on on our class we did on georeferencing and mapping, some of the students are already sending in. This is Augustine Mensa. I will reach out to him personally, so I have a gift for him. This is his map, and we have another person, Adeniji, who has submitted it. This is the data set we sent, and this is the tutorial we had yesterday. This is to tell you that people are really participating. So we appreciate this. If there is any correction, of course, we will make on the map. We'll reach out to you. We'll try as much as we can to add you to our mentorship section. We always have mentorship section in African Women in GIS. So we are going to add you to our mentorship section so that you can improve on what you do. So we really appreciate you sending in this across to us. So we'll look forward to seeing you tomorrow. Thank you once again. So please don't forget to register if you have not. Remember, we are giving our certificate, and remember, the certificate is free and the training is free. So thank you so much for your patience and thank you for joining us. We appreciate it. See you tomorrow, 6 p.m. GMT +1.
Nina.